Good morning. Welcome back. We are now discussing a concept of determination of the moduli of elasticity, that is Young's modulus, rigidity modulus, bulk modulus, and the Poisson's ratio by a method known as Searle's double bar. This Searle's double bar consists of two identical metal rods or metal bars A and B, and which are having square cross sections, and the experimental wire XY is rigidly fixed to the bars at the midpoints as shown in figure. So first of all, we are determining Young's modulus of this wire XY, and for that we have considered two bars A and B, and two bars are independently suspended with the help of threads as shown in figure from a rigid support. And when the two bars are brought near as shown in the second figure and released, they execute simple harmonic motion in a horizontal plane, and the time of vibration will depend upon the moment of inertia of the oscillating system, dimensions of the experimental wire, and Young's modulus of the wire. Let theta be the angle through which each bar is displaced at any instant of time as shown in figure B. You can see here are the thetas. Then if R is the radius of curvature of the wire, R is radius of the curvature of the wire, and L is length of the wire, that is XY, then therefore L will be equal to R into 2 theta, or R radius of curvature will be equal to L by 2 theta. That is, therefore, restoring couple is equal to bending moment of the wire, and that will be equal to minus Qi by R, or that is minus Q into AK square by R, or that is minus Q AK square by L into 2 theta. The negative sign indicates that the restoring couple is directed towards the undisturbed portion of the bars. If I is the moment of inertia of each bar about the suspended wire, and d square theta by dt square is the angular acceleration, then the couple acting on each bar will be equal to I into d square theta by dt square, and at equilibrium, bending moment of the wire will be equal to couple acting on each wire, and therefore I into d square theta by dt square is equal to minus q a k square by L into 2 theta, or I into d square theta by dt square plus 2 a k square by L into theta equals 0, or this can also be rewritten as d square theta by dt square plus 2 q a k square by I L into theta equals 0, and this will be in the form d square x by dt square plus omega square x is equal to 0, which is the expression for simple harmonic motion. And therefore, as the two equations are similar, it is clear that the motion of the bars is simple harmonic in nature, and the period of oscillation of the bars is therefore given by the expression T1 is equal to, and comparing this with the standard expression and simplifying, we get T1 is equal to 2 pi into root of IL by 2 Q A K square, and T1 square is equal to therefore 4 pi square into IL by 2 Q A K square, and therefore rewriting this we get Q, that is expression for Young's modulus, Q equals 4 pi square IL by 2 T1 square AK square. For a wire of circular cross section of radius A, AK square will become pi a power 4 by r, and therefore this expression can be rewritten as q equals 8 pi il divided by a power 4 t1 square. And here t1 is the time period of oscillation and a is the radius of curvature of the wire, and the time period of oscillation can be determined by taking the time for a definite number of oscillations, say 10 or 20. The radius of the wire is determined using screw gauge. Moment of inertia of the bar can be calculated by determining its mass as well as the dimensions, that is length and breadth. For a bar of square cross section having a mass m, length L, breadth B, the moment of inertia is given by the expression I is equal to m into L square plus B square by 12. Now coming to the rigidity modulus, using the same experimental setup, we are now trying to determine the rigidity modulus of the wire. And in order to determine the rigidity modulus of the wire, one of the bar, say bar A, is horizontally clamped as shown in figure, whereas the bar B hangs below the bar A, and the bar B is slightly displaced and slightly rotated, and it is made to execute the torsional oscillations. The period of oscillations is taken as equal to T2 for this case, and it is determined by taking the time for a definite number of oscillations. And T2 is given by the expression T2 is equal to 2 pi into root I by C, where C is the couple per unit twist of the wire, and it is given by the expression C is equal to pi eta a power 4 by 2L, where A is radius of the wire xy and eta is its rigidity modulus. And therefore, substituting the value of C in the above expression, therefore T2 becomes equal to 2 pi into square root of 2IL divided by pi eta a power 4, or T2 square is equal to 8 pi square IL by pi eta a power 4. And therefore, finally, the rigidity modulus eta is equal to 8 pi IL divided by T2 square a power 4. So by knowing this expression, by knowing the moment of inertia of the rod, by knowing its length, so by knowing length of the wire and radius of the wire, and by knowing the time period of oscillation, we can determine the rigidity modulus of the wire. So if we know the rigidity modulus as well as Young's modulus, we can easily determine the bulk modulus of the material of the wire using the expression K equals Q eta by 9 eta minus 3Q. By knowing Young's modulus and rigidity modulus, one can determine bulk modulus using this expression. Now coming to the Poisson's ratio, we have the expression for rigidity modulus in terms of Young's modulus and Poisson's ratio, that is eta is equal to Q divided by 2 into 1 plus sigma. Or rewriting this, we get sigma is equal to Q by 2 eta minus of 1. Substituting the expressions for Q and eta in the above expression, we get Q equals 8 pi IL by a power 4 T1 square into half into T2 square a power 4 divided by 8 pi IL minus of 1, and simplifying we get sigma is equal to T2 square by 2 T1 square minus of 1. So by knowing the time periods T1 and T2, so we can evaluate or we can determine the Poisson's ratio sigma using this expression. So coming to the advantages of the Searle's double bar method is that the values of elastic moduli can be determined by measuring the time periods T1 and T2. Only small length of the specimen will be enough and that should be in the form of wire. If we have the specimen, a small quantity of specimen in the form of a wire, then we can determine all the moduli of elasticity along with Poisson's ratio. Since the time period of oscillation can be measured accurately, the calculation of elastic moduli will be simple as well as it will be accurate. Thank you.